At Saturn's North Pole, there is a storm the size of 4 Earths. It has been there for at least 40 years, possibly much longer, and it is shaped like a perfect hexagon. 6 equal sides, 6 equal angles, symmetric to within measurement error, stable across decades of chaos and hurricane-force winds. On Earth, no storm ever holds a shape like that. Every hurricane curves into a spiral. Every vortex bends and meanders. Fluid physics says geometric precision should collapse immediately into chaos. But Saturn never got that memo. And when the James Webb Space Telescope stared at this impossible shape for 10 straight hours in 2024, it found something even stranger: structures high above the hexagon that nobody expected, that nobody can explain, and that nobody has ever seen on any other planet. If this video sparked even one new thought about the universe, a like costs nothing but helps everything for a small team trying to reach more curious minds. In 3, 2, 1, liftoff. Close your eyes for a moment and picture a storm. Not a light spring shower, a real storm. The kind that earns a name, the kind that satellites track from orbit, the kind that reshapes coastlines and rewrites insurance policies. Picture a hurricane spinning somewhere over warm tropical water, that massive swirling disk of cloud and wind rotating slowly, like a pinwheel the size of a small country. Now, picture a typhoon in the Pacific, a cyclone in the Indian Ocean, a polar vortex draped over the Arctic like a slow-breathing cap of cold air. Look at all of them from space. Look at every storm system Earth has produced in all of recorded history, every weather pattern that meteorologists have photographed, measured, and modeled across generations of atmospheric science. Notice the shapes. They are all, without exception, round, curved, circular or roughly circular. They spiral, they meander, they bend. Even when a storm is not a perfect circle, it is a curve, and that curve wraps back on itself. It never closes into a corner. It never turns at a sharp angle. Fluid physics does not produce sharp angles. The mathematics of rotating gases and liquids, the equations governing how pressure and velocity interact in a spinning system, they do not write corners into the answer. They write arcs, always arcs. This is not a quirk of Earth's particular atmosphere. This is a fundamental consequence of how fluids behave when they spin. When a parcel of gas moves in a rotating system, the forces acting on it, pressure gradients, rotation, internal viscosity, conspire to produce curved motion. The Coriolis effect, the apparent deflection of moving air caused by a planet's rotation, bends trajectories into spirals. Even in the most extreme and violent atmospheric systems we know, the outcome is rotational symmetry. Circles, ovals at their most distorted. The fluid universe does not seem to permit anything else, which is why what sits at Saturn's North Pole has been making atmospheric scientists deeply uncomfortable for over 4 decades. At 78 degrees north latitude on the planet Saturn, locked in place above the cloud tops like something drawn there with a compass and a ruler, there is a hexagon, not a metaphorical hexagon, not a rough approximation of six-sidedness that you have to squint at and tilt your head to see. A genuine, confirmed, geometrically regular six-sided structure with sides and angles so consistent that researchers measuring them from spacecraft have described the symmetry as extraordinary. 6 sides of approximately equal length, 6 corners turning at approximately equal angles, rotating as a unit with a period so stable it has been clocked to within seconds. persisting, as far as we can tell, for at least 40 years of continuous observation, possibly much, much longer. The dimensions alone are enough to stop conversation. Each side of this hexagon measures approximately 14,500 kilometers in length. 14,500 kilometers. For comparison, the diameter of the Earth, the distance from one side of our planet to the other, straight through the center, is approximately 12,700 kilometers. That means each individual side of Saturn's hexagon is longer than Earth's full diameter by nearly 2,000 kilometers. The hexagon as a whole spans approximately 30,000 kilometers from one side to the other. Nearly 4 full Earths could be set side by side inside the width of this structure, and they would fit with room to spare. Inside the hexagon, inside its interior, sits a polar vortex whose eye alone spans approximately 2,000 kilometers, roughly the distance across the continental United States from Chicago to the Atlantic coast. And the whole system is not just a surface pattern. It extends downward through the atmosphere by approximately 300 kilometers below the cloud tops, possibly much deeper into regions of Saturn's atmosphere, where pressures exceed anything at Earth's surface by orders of magnitude. The winds inside the hexagon's jet stream move at approximately 320 kilometers per hour. That is roughly equivalent to the fastest wind speeds ever recorded in the most violent terrestrial hurricanes. Sustained, not in a brief gust, but continuously across a structure that stretches across an area larger than our entire planet's disk. And those winds do not meander. They do not wobble and drift. They maintain their hexagonal path with a consistency that no weather pattern on Earth approaches. The hexagon rotates. The entire structure turns with a period of 10 hours, 39 minutes, and 24 seconds. That number sounds specific, and it is specific because it matches almost precisely the rotation period inferred from Saturn's radio emissions generated deep within the planet's interior, in regions we cannot directly observe. This alignment between the hexagon's rotation rate and the internal rotation rate of the planet itself is not a coincidence that researchers brush aside. It is a clue buried inside a mystery, a data point that ties a visible atmospheric structure to the hidden interior of an alien world in ways that science has not fully untangled. Now, take all of that and sit with it for a moment. A hexagon, 4 Earths wide, winds at hurricane force, 300 kilometers deep, rotating in synchrony with Saturn's interior, stable for at least 40 years. On a planet with no solid surface, no coastlines, no land masses to anchor or deflect airflow, nothing but an ocean of gas under crushing pressure, swirling at wind speeds that make Earth's atmosphere seem placid by comparison. How is this possible? That question is the engine of everything that follows. But before we chase the answer, we need to understand the full weight of the question itself, because the impossibility of the hexagon is not just about the shape. It is about everything that the shape implies, about the planet it sits on, and the physics it seems to defy. To feel the real strangeness of Saturn's hexagon, you first need to understand something about Saturn itself, because Saturn is already one of the most alien worlds in our solar system before you even get to the hexagon. It is a planet that operates at extremes so far beyond Earth's experience that almost nothing about it is intuitive. Saturn is the 6th planet from the Sunday. It orbits at an average distance of approximately 1.5 billion kilometers, which means that sunlight reaching Saturn has already traveled 9 times farther than the sunlight reaching Earth. By the time it arrives, it is dramatically weaker. Saturn receives roughly 1% of the solar energy per unit area that the equator of Earth receives. The planet is cold by terrestrial standards in its upper cloud layers, with temperatures in the visible cloud decks dropping to approximately -178 degrees Celsius. But it is not simply a cold, dead world. Saturn generates more heat from within itself than it receives from the Sun, radiating nearly 2.5 times as much energy outward as it absorbs. This internal heat, thought to arise partly from the slow gravitational compression of helium droplets raining down through Saturn's interior, drives atmospheric circulation from below in ways that have no real parallel in Earth's weather. Saturn is enormous. Its equatorial diameter is approximately 120,500 kilometers, making it the second largest planet in the solar system, surpassed only by Jupiter. But here is the detail that never stops being strange. Saturn is the least dense planet in the solar system. Its average density is approximately 0.7 grams per cubic centimeter. The density of water is 1 gram per cubic centimeter. This means that if you could find a bathtub of planetary scale filled with water, Saturn would float in it. The planet is composed overwhelmingly of hydrogen and helium, the lightest elements, with trace amounts of other compounds including methane, ammonia, and water ice. It has no solid surface in any meaningful sense. What we call Saturn's surface is simply the level at which the atmosphere becomes dense enough that we can no longer see through it. Below that, the pressure and temperature increase steadily as you descend, the hydrogen gas gradually becoming liquid, eventually transitioning to a state of metallic hydrogen under pressures so extreme that the element conducts electricity like a metal. The atmosphere above that interior ocean of liquid hydrogen is deep, vastly deeper than Earth's thin shell of breathable air. Saturn's atmosphere extends for hundreds of kilometers above the visible cloud layers, and it is churned by winds that are among the fastest in the solar system. Near Saturn's equator, wind speeds reach approximately 1,800 kilometers per hour. That is 5 times the speed of the most powerful hurricane-force winds ever recorded on Earth. These are not temporary gusts. These are sustained wind speeds across a planet-girdling belt, maintained by the combination of internal heat, differential rotation, and the dynamics of a gas giant's layered atmosphere. It is into this context, this world of crushing pressures, extreme temperatures, no solid surface, and winds that would make any terrestrial storm seem like a gentle breeze, that you must place the Hexagon. A geometry problem carved into the atmosphere of a gas giant by physics alone. No walls, no mountains, no land to force the air into a shape, just gas, rotating and somehow arranging itself into 6 equal sides that have remained equal for decades. To understand why this is remarkable, consider what storms normally need in order to maintain any kind of shape at all. On Earth, large weather systems are shaped and constrained by the planet's geography. Mountain ranges deflect wind patterns. Continent and ocean boundaries create temperature contrasts that drive circulation. Even the relatively smooth surfaces of the ocean create friction that influences how air moves above it. Earth's polar vortex, the large area of cold air and low pressure that sits over the Arctic during winter, is not perfectly circular. It wobbles, stretches, and distorts. It breaks down and reforms. When meteorologists describe the polar vortex becoming unstable and sending blasts of Arctic air down into lower latitudes, they are describing exactly this kind of natural deviation from symmetry. The polar vortex is as close to a sustained circular atmospheric feature as Earth produces, and it is consistently imperfect, always in motion, always losing its shape at the edges. Saturn has none of the geographic anchors that Earth relies on. No mountains, no continents, no boundary between land and sea. Its surface, to the extent that it has one, is a fluid in motion. And yet, this hexagon sits there, geometrically precise, for decade after decade, while the rest of Saturn's atmosphere roils around it in the kind of turbulent chaos you would expect from a planet of this size, composition, and energy budget. The question of why this particular storm holds its shape while every other storm system in the solar system does not, is not just a Saturn question. It is a question about the fundamental rules of fluid dynamics in a rotating system. It is a question about what conditions can produce and sustain geometric order inside a system that should be dominated by turbulence. And it is a question that, even after 40 years of observation by some of the most sophisticated spacecraft ever built, does not yet have a fully complete answer. But before we arrive at the answer, we need to go back to the beginning, to a cold spacecraft flying past a distant planet in the winter of 1981, capturing images of something it could not quite resolve, but that no one who looked at the data could quite explain. Because the story of the hexagon is also the story of how science encounters the unexpected, how researchers respond when an observation refuses to fit any existing model, and how the slow accumulation of better instruments and better data eventually transforms a mystery from incomprehensible to almost understood, while simultaneously revealing that it is stranger than anyone initially suspected. The Voyager program was one of the most ambitious undertakings in the history of planetary exploration. Launched in the summer of 1977, Voyager 1 and Voyager 2 were identical spacecraft designed to take advantage of a rare alignment of the outer planets that would allow a single spacecraft, using gravitational assists, to visit Jupiter, Saturn, Uranus, and Neptune in a single extended mission. The geometry of this alignment would not recur for another 176 years. NASA took the opportunity. The result was two spacecraft that between them revolutionized our understanding of the outer solar system, discovering active volcanoes on Jupiter's moon Io, revealing the complexity of Saturn's ring system, imaging the bizarre, tilted world of Uranus, and sending back the first close-up photographs of Neptune's dynamic atmosphere. When Voyager 1 flew past Saturn in November of 1980, it was moving fast. A flyby mission does not linger. The spacecraft swept through the Saturn system over the course of a few days, making observations with its suite of scientific instruments, transmitting data back across the roughly 1.5 billion kilometers of space between Saturn and Earth. The images it sent back were extraordinary by the standards of the time, the best photographs of Saturn ever taken, vastly superior to what telescopes on the ground could achieve. They revealed the ring system in intricate detail, showed the surfaces of several moons, and captured the disk of the planet itself in ways that no human eye had ever seen. Among the data recorded by Voyager 1 during this flyby were images of Saturn's north polar region. The polar regions of gas giants are interesting targets because they are the sites of some of the most unusual atmospheric activity: polar vortices, aurora, cloud structures driven by the planet's internal heat rather than by sunlight. The north polar region of Saturn was partially in shadow during the Voyager 1 encounter, which limited what the cameras could capture in visible light. But the spacecraft's instruments recorded data at multiple wavelengths, and in some of those records there was something strange. something in the cloud patterns near the North Pole that did not look like the smooth, curved structures that dominated the rest of Saturn's atmosphere. Voyager 2 made its own Saturn flyby in August of 1981, passing through the Saturn system from a different angle and adding to the dataset. The two spacecraft together had captured a substantial record of Saturn's atmosphere, but analyzing the data was a years-long process. The images had to be processed, calibrated, corrected for various instrumental effects, and then interpreted by researchers who were simultaneously trying to understand an entirely new atmospheric system about which they knew almost nothing. It was not a process that rewarded hasty conclusions. It was not until 1987 that a planetary scientist named David Godfrey, working at the National Oceanic and Atmospheric Administration in Boulder, Colorado, formally identified what the Voyager data had been hiding. Godfrey was piecing together multiple Voyager images of Saturn's North Polar region, assembling them into composite views that allowed the cloud structure to be seen more clearly than any individual image permitted. What he found when those images were assembled and examined carefully was something that initially seemed so improbable that the word astonishing barely covers the reaction it provoked. There, at approximately 78 degrees north latitude, clearly visible once you knew to look for it, was a hexagonal cloud pattern, 6 sides, rotating, stable across the multiple images captured during the 2 Voyager flybys. A geometric regularity that had no precedent anywhere in the study of planetary atmospheres. Godfrey published his finding in the journal Icarus in 1988. The paper was careful and measured in its language, as good scientific papers should be. But the finding itself was anything but measured. Here was a structure that should not, by any conventional atmospheric physics reasoning, be able to exist in the form it took. And it was not a small structure. Based on the Voyager data, Godfrey's initial estimates of the hexagon scale were roughly consistent with what later, more precise measurements would confirm. This was a feature of planetary proportions, not a local atmospheric quirk. The scientific community's reaction was a mixture of fascination and skepticism. Skepticism because extraordinary claims require extraordinary evidence, and the Voyager data, while real, was limited. The polar region had been partially in shadow. The images were not as sharp as scientists would have liked. The hexagon appeared in the data, but was it truly a geometric hexagon, or was it an artifact of image processing, or a coincidental arrangement of cloud features that merely suggested a hexagonal outline? These were reasonable questions. Science asks them by default when confronted with anomalous results. The problem was that there was no way to easily resolve those questions in 1988. Saturn was 1.5 billion kilometers away. The only spacecraft that had visited it had already passed through the system and were now on their way to the outer solar system, never to return. Earth-based telescopes of the era, even the best available, did not have the resolution to image Saturn's polar regions at the detail needed to confirm or refute what the Voyager data suggested. Saturn's North Pole is not even easy to observe from Earth because it is tipped away from our line of sight during much of Saturn's year, and the northern polar region requires Saturn to be at a favorable orbital position for direct observation. And so the hexagon sat, confirmed in the data but unverifiable by new observation, generating theoretical speculation but no new empirical evidence for nearly 2 decades. Researchers who worked on outer planet atmospheres kept it in mind. It appeared in review papers, in conference discussions, in the occasional theoretical study. But Without new data from a spacecraft that could observe Saturn's North Pole directly, at high resolution, over an extended period of time, the hexagon remained tantalizing rather than understood. The Hubble Space Telescope, launched in 1990, provided some contribution. Hubble's observations of Saturn could not match the resolution of a dedicated spacecraft in orbit around the planet, but they offered something Voyager had not: repeated observations over time. Hubble confirmed that the hexagon was still present when Saturn's North Pole came into observable alignment. It had not dissipated. It had not changed its overall form in ways that Hubble could detect. The structure that Voyager had glimpsed in 1981 and that Godfrey had formally identified from archive data in 1987 was still there years later. This persistence was itself a finding. It narrowed the range of possible explanations. Whatever this structure was, it was not a transient weather event. It was stable on timescales of years, possibly decades, possibly longer. Hubble observations of Saturn's South Pole during this same era also contributed an important piece of information. They confirmed, as clearly as the instruments allowed, that the South Pole of Saturn does not have a hexagon. It has a polar vortex, as both poles do, but the South Pole's vortex is circular. It is the kind of large-scale atmospheric feature that planetary scientists expected to find at the poles of a gas giant, a rotating cyclonic system without geometric corners. The hexagon is a feature of Saturn's North Pole only. The asymmetry between the two poles is itself a scientific puzzle. Why does one pole have a hexagon and the other a circle? What is different about the atmospheric conditions at the North Pole that produces a geometrically stable polygon, while the South Pole, subject to the same planetary rotation and presumably similar overall atmospheric physics, produces a circular vortex instead? This north-south asymmetry became one of the constraints that any successful theoretical explanation of the hexagon would need to address. The long wait ended on October 15th, 1997, when NASA launched the Cassini-Huygens spacecraft. Cassini was a fundamentally different kind of mission than Voyager. It was not a flyby. It was a dedicated Saturn orbiter designed to spend years circling the planet, making repeated observations of its atmosphere, its rings, and its moons from an orbit that could be adjusted to target specific features at specific times. If Voyager was a fast drive-through of the Saturn system, Cassini was a years-long residency. The spacecraft carried an array of scientific instruments that represented decades of technological advancement over Voyager's hardware cameras, capable of imaging at much finer resolution, spectrometers that could probe the chemical composition of the atmosphere, instruments designed specifically to detect and characterize the kinds of atmospheric features that planetary scientists had learned to look for in the years since the Voyager encounters. Cassini arrived at Saturn in July 2004 and entered orbit, beginning what would eventually become a 13-year mission. The science that followed from that mission transformed planetary science across multiple fronts. But for the hexagon, Cassini's arrival came with an immediate complication. Saturn's North Pole was in winter darkness when Cassini arrived. The planet's obliquity, the tilt of its axis, means that its polar regions experience long seasons, and the North Pole was tilted away from the sun, receiving no direct sunlight. This was not a crisis for the mission, because Cassini carried instruments that could observe in infrared wavelengths, detecting heat rather than reflected light. Infrared observations could reveal atmospheric structure through thermal emission, the heat generated by Saturn's interior, radiating upward through the atmosphere, even when visible light was unavailable. Using its visual and infrared mapping spectrometer, Cassini made the first high-quality thermal infrared observations of Saturn's north polar region beginning in 2006. What it found confirmed the hexagon beyond any remaining doubt. The hexagonal structure was there, clearly defined in the thermal data, its shape revealed by the pattern of clouds seen in silhouette against the infrared glow of Saturn's interior heat. These images were of dramatically higher quality than the Voyager data. The hexagon's corners were sharper, its sides more clearly delineated, its interior structure more detailed. Inside the hexagon, the Cassini instruments revealed a large-scale cyclonic polar vortex with an eye, a central clear region surrounded by a wall of clouds that was itself remarkable in scale. That approximately 2,000-kilometer wide eye mentioned earlier, ringed by cloud towers and driven by winds that Cassini measured at speeds exceeding 500 kilometers per hour at the vortex wall. The thermal infrared data also revealed something that the Voyager observations had not clearly shown. The hexagon extended significantly below the visible cloud tops. The feature was not just a surface pattern painted on the upper atmosphere. It reached downward, with the same hexagonal structure detectable at pressure levels well below the visible cloud layer. Cassini's instruments estimated the hexagon extended approximately 100 kilometers below the cloud tops in their initial analysis, with later work suggesting the depth might be considerably greater. This depth was significant. A shallow surface feature and a deep, vertically coherent atmospheric structure required different physical explanations. The hexagon's depth implied that whatever mechanism was creating and sustaining it had to be operating through a substantial vertical extent of the atmosphere, not just at a single level. What the thermal data could not provide was color. For that, Cassini needed the hexagon to come into sunlight. Saturn's northern polar spring arrived slowly. As everything on Saturn does, the planet's year is approximately 29 Earth years long, which means each of its 4 seasons lasts roughly 7¼ Earth years. As Saturn moved through its orbit, the North Pole began to tilt toward the Sun, and the polar winter that had kept the region in darkness gradually gave way to the arriving polar spring. By January 2009, sunlight had reached Saturn's North Polar region, and Cassini's visible light cameras, the imaging science subsystem, could finally see the hexagon in reflected light, in color, for the first time since the limited Voyager observations nearly 3 decades earlier. The images that came back were extraordinary in a way that went beyond their scientific content. They were visually stunning. Saturn's hexagon in color and high resolution is one of the most striking images. The Cassini mission produced a massive geometric form in golden, tan, and white cloud tones, sitting at the top of a planet like an architectural feature rather than a weather system. The precision of the shape is immediately apparent to the naked eye. The corners look like corners. The sides look like sides. It does not look like something a planet made. It looks like something built. That appearance, the appearance of deliberate construction, is part of what makes the hexagon so psychologically striking, and part of what has made it an enduring object of public fascination since those first color images began circulating. The human brain is extraordinarily good at detecting geometric regularity, which is exactly why irregular patterns look irregular to us, and exactly why a hexagon on a gas giant makes the visual system fire differently than a round storm does. The brain pattern matches to human artifacts, to honeycombs, to architectural tiles, to shapes that we associate with intentional design. Seeing a hexagon on a planet, therefore, produces a cognitive jolt that a circular storm does not. The storm matches our expectation. The hexagon violates it. This psychological dimension is worth dwelling on for a moment, not because it explains the hexagon, but because it shapes the conversation around it. The hexagon has attracted more popular fascination, more wild speculation, and more breathless internet theorizing than almost any other single feature in the solar system. Theories involving alien construction, deliberate geometric signaling, mystical significance, and various other non-physical explanations have circulated widely in the years since the high-resolution Cassini images became public. The hexagon looks too perfect, the reasoning goes, and therefore it must be artificial in some way. This reasoning is incorrect, and the actual explanation, which we will reach in detail, is far more elegant than any artificial construction hypothesis, because it emerges entirely from physics. But understanding why that incorrect reasoning feels compelling helps explain why the hexagon is such a powerful scientific story. It forces the universe to prove that physics can produce what looks like geometric intention without any intention at all. The Cassini visible light observations of 2009 and the years that followed produced a dataset of extraordinary richness. For the first time, scientists could track the motion of individual cloud features within and around the hexagon, measure wind speeds at different latitudes and depths, and follow the evolution of the structure over time. What they found reinforced the picture that had been building since the first infrared observations. The hexagon was far more complex than a simple geometric outline. It was a multi-layered, dynamically active system with internal structure, with a central polar vortex that had its own organization distinct from the jet stream forming the hexagon's walls, with cloud features inside the hexagon that moved differently from features outside it, and with behavior at its boundaries, the corners, specifically, that generated intense local turbulence and spiral eddies as the jet stream air negotiated its way around each turn. The corners of the hexagon deserve special attention because they represent the most physically interesting parts of the structure. In a straight jet stream, air moves smoothly along its path without major directional changes, but the hexagon's jet stream turns 6 times, at 6 corners, each turn representing a significant change in direction for fast-moving air masses. At each corner, the flow dynamics become complex. Observations show spiral vortices forming at the hexagon's corners, eddies generated by the shear and curvature of the jet stream as it navigates the turn. These eddies are themselves substantial weather features, hundreds of kilometers across, spinning in the opposite sense to the overall cyclonic rotation of the polar vortex. They are a predictable consequence of the corner geometry, and their presence in the observational data was one of the confirmations that the hexagon's shape is maintained by a genuine physical mechanism, rather than being a visual artifact of any kind. The overall rotation of the hexagon is also worth dwelling on more carefully. The hexagon as a unit, the pattern of the wave, not the individual parcels of gas that make up the jet stream, rotates with that clockwork period of 10 hours, 39 minutes, and 24 seconds. This is the rotation rate of the hexagonal pattern, the standing wave or oscillation that defines the geometric shape. The gas molecules that make up the jet stream are themselves moving much faster than this. They are the wind at 320 kilometers per hour, but the pattern they inscribe in the atmosphere rotates much more slowly, tracking almost perfectly with Saturn's interior rotation rate. This distinction between the motion of the material and the motion of the pattern is fundamental to understanding what the hexagon actually is, and it is a concept we will return to in considerable depth when we examine the physics. For now, the key point is that the hexagon's rotation rate connects it to something deep inside Saturn, to a rotation that we cannot directly observe, but can infer from the radio waves that Saturn's interior generates. That connection is one of the hexagon's most tantalizing aspects, and one of the most consequential clues to its origin. The scale of what Cassini's observations revealed grew steadily richer through the early years of the mission. Researchers studying the hexagon data found that the feature acts as more than just a visual boundary. It functions as a dynamic barrier in the atmosphere, a boundary that separates the chemistry and cloud physics of its interior from those of the surrounding atmosphere. The air inside the hexagon and the air outside it are not identical. They have different compositions, different cloud particle size distributions, different concentrations of haze particles. The hexagon's jet stream appears to act as a kind of wall that prevents large-scale mixing between the polar interior and the mid-latitude atmosphere surrounding it. This chemical isolation is itself a remarkable property. Earth's polar vortex, its closest terrestrial analog, similarly isolates polar air chemistry from mid-latitude air. This is the mechanism by which the Antarctic ozone hole forms and is maintained. But Earth's polar vortex is imperfect, leaky, and seasonally unstable. Saturn's hexagon appears to maintain its barrier function with greater fidelity over longer timescales and across a much larger spatial scale than anything Earth's atmosphere produces. This barrier function has implications for how the interior of the hexagon evolves over time, for what chemistry occurs there under relative isolation, and for what happens to the clouds and hazes that form inside it. These implications became directly relevant when Cassini's cameras recorded one of the hexagon's most dramatic observed behaviors, a systematic change in color that unfolded over the course of 4 years, and that generated its own wave of scientific discussion when it was publicly revealed. But the physical reality of the hexagon, the sheer fact of its existence, its dimensions, its stability, its connections to Saturn's interior, is the foundation on which everything else rests. And sitting with that foundation for a moment before proceeding is worthwhile, because the hexagon is not a small anomaly tucked away in an obscure corner of planetary science. It is a confirmed observational reality that forced every existing model of atmospheric dynamics to confront a phenomenon those models had not predicted. Every atmospheric physicist who encountered it for the first time faced the same uncomfortable realization: the existing tools and frameworks were insufficient. Not wrong in their basics, but incomplete in their application to the conditions at Saturn's North Pole. The hexagon did not break physics. It revealed that physics, fully applied, could produce outcomes far more geometrically ordered than intuition suggested. That realization that order can emerge from chaos under the right conditions, that geometry can be written into a storm by physics alone, is the first and most important thing the hexagon has to teach. And it teaches it simply by existing, in full view of every instrument we have trained on it, undeniable, precise, and entirely natural. The Voyager spacecraft glimpsed it first, in data that took years to properly analyze. Cassini confirmed it, detailed it, and watched it change. And it was only when those changes began to accumulate changes in color, changes in altitude, changes revealed layer by layer, as Cassini's instruments probed deeper and higher that scientists began to understand that the hexagon they had been looking at was only the most visible layer of something far more vertically extensive than they had imagined. That understanding deepened slowly, observation by observation, data release by data release, through the long years of the Cassini mission. And what it revealed about the hexagon's behavior across Saturn's seasons, including one of the most visually dramatic changes a spacecraft had ever documented in a planetary atmosphere, is where the next chapter of this story begins. Science rarely delivers its revelations in the clean, linear sequence that textbook narratives imply. The story of Saturn's hexagon did not unfold as a series of steadily mounting certainties, each discovery fitting neatly onto the previous one, building toward a tidy conclusion. It unfolded in the way most real science does, in fragments, in surprises, in observations that answered one question by generating three new ones, and in the slow accumulation of a picture that kept proving stranger and more complex than the previous version of itself. The hexagon that Cassini was studying in the years after 2009 was not simply the hexagon that Voyager had glimpsed and Godfrey had identified. It was a living system, and like any living system, it changed. Some of those changes were subtle, some were anything but. By the time Cassini began making its visible light observations of the hexagon in 2009, the spacecraft had already been at Saturn for 5 years. In those 5 years, the mission had rewritten the scientific understanding of the Saturn system many times over. Cassini had revealed that Saturn's moon Enceladus was geologically active, venting plumes of water, ice, and organic compounds from cracks in its southern polar region. It had mapped the extraordinary diversity of Saturn's ring system in unprecedented detail. It had dropped the Huygens probe into the atmosphere of Titan and received data back from that fog-shrouded moon's surface. The mission's scientific harvest was extraordinary by any measure. And now, as the North Polar Spring brought sunlight to the hexagon, Cassini's most capable cameras were finally trained on the feature that had been waiting in the dark since the spacecraft arrived. The images that came back from Cassini's imaging science subsystem beginning in 2009 showed the hexagon in a color that was, in retrospect, not what anyone had necessarily expected. A deep, striking blue. The interior of the hexagon, the region of atmosphere enclosed within the six-sided jet stream, appeared predominantly blue in the color composite images that Cassini's camera produced. It was not a pale or ambiguous blue. It was a rich, distinctly blue coloration that contrasted sharply with the golden, tan, and ochre tones of Saturn's lower latitude cloud bands. The hexagon itself, the jet stream boundary, appeared as a bright, complex ribbon of clouds, and surrounding it at lower latitudes, Saturn's atmosphere carried its familiar banded appearance. But inside the hexagon, the atmosphere was blue. The blue coloration was real, not an artifact. Cassini's cameras observe in multiple wavelengths, and the color composite images are constructed from those multi-wavelength observations in ways that accurately represent the true spectral character of what the cameras detect. The blue of the hexagon's interior was confirmed to be a genuine atmospheric phenomenon, reflecting the scattering of sunlight in a particular way through the cloud and haze structure of the polar atmosphere. The leading explanation, and it is important to note that this remains a scientific interpretation rather than a perfectly proven mechanism, is related to the size and concentration of aerosol particles in the polar atmosphere. Small atmospheric particles scatter shorter wavelengths of light more efficiently than longer wavelengths, producing blue colorations, while larger particles or denser hazes produce yellower or redder tones. The interior of the hexagon appeared to contain relatively few of the larger haze particles that dominate Saturn's lower latitude atmosphere, leaving a cleaner, particle-sparse atmosphere in which light scatter produced the observed blue. One proposed reason for this particle deficit connects directly to the hexagon's role as an atmospheric barrier. If the jet stream wall of the hexagon genuinely restricts the transport of large aerosol particles from the surrounding atmosphere into the polar interior, if it functions as a chemical isolation boundary as well as a dynamic one, then the interior of the hexagon would have been cleared of larger particles during the long polar winter, when there was no sunlight to drive the photochemical reactions that produce new aerosol particles. The interior atmosphere, isolated and dark for years, would gradually have lost its heavier aerosol load, becoming relatively clean and particle-poor. When sunlight finally arrived with the northern spring, this particle-sparse interior would have scattered light to produce the observed blue. Outside the hexagon, where the atmosphere was not similarly isolated, larger particles from lower latitudes could mix in, and the atmosphere retained its more typical golden hue. This explanation is coherent and consistent with what Cassini observed. But it is not the only possible explanation, and researchers have been careful to note that the precise mechanisms of aerosol formation, transport, and evolution in Saturn's atmosphere are not perfectly understood. The blue coloration of the hexagon interior, while explained in outline, belongs to the category of phenomena that are understood in principle without being fully characterized in detail. It is a pattern in the data that fits with a physical story, even if every parameter of that story has not been precisely measured. What made the blue coloration even more scientifically interesting was what happened to it next, because the hexagon did not stay blue. Between 2012 and 2016, a span of 4 Earth years, which is less than half of a single Saturn season, Cassini's cameras recorded a systematic change in the color of the region inside the hexagon. The blue gradually gave way to gold, not overnight, not in any sudden transition. Over the course of those 4 years, the deep blue of the polar interior slowly warmed in tone, shifting through intermediate colors, and by September of 2016, when Cassini's cameras recorded the North Polar region again in comparable imaging conditions, the interior of the hexagon had become a distinctly golden, yellowish hue, similar in tone to the rest of Saturn's atmosphere at lower latitudes. Though not identical, the transformation was dramatic enough to be immediately apparent when the two images from 2012 and 2016 were placed side by side. The same planet, the same pole, the same hexagon, completely different colors. NASA released these comparison images publicly in October 2016, and the reaction was significant. The images were visually striking, a before and after, that showed something substantive happening in Saturn's atmosphere over a human observable timescale. But they also raised an immediate and obvious question: what caused this? Why would the interior of the hexagon change from blue to gold over the course of 4 years? The leading hypothesis offered by Cassini researchers connects the color change to Saturn's seasonal cycle. Saturn's North Pole was experiencing spring and moving towards summer during this period. As Saturn moved along its orbit, the amount of sunlight reaching the North Polar region was increasing steadily. More sunlight means more energy available to drive the photochemical reactions that produce haze particles in the atmosphere. Photochemistry in planetary atmospheres operates through reactions triggered by ultraviolet radiation from the sun, reactions that convert simple molecules into more complex organic compounds that eventually condense into the small, solid or liquid particles that make up atmospheric hazes. When there is more sunlight, there is more photochemical activity, and more photochemical activity means more haze production. The proposed mechanism works like this. As northern spring brought more sunlight to the polar region, the photochemical production of haze particles inside the hexagon began to increase. New particles formed inside the hexagon's isolated interior, building up over time. As the concentration of these freshly produced haze particles grew, their light-scattering properties changed the observed color of the interior atmosphere. Small, freshly produced particles would initially contribute a blue tint, but as those particles aged, coagulated, and grew larger, or as they interacted with other atmospheric compounds, the scattering characteristics shifted toward longer wavelengths, producing the warmer, yellower tones observed in 2016. The hexagon itself may have contributed to the transformation by continuing to act as its characteristic atmospheric barrier. If the jet stream wall prevented large-scale mixing between the interior and exterior atmospheres, then the chemistry of the interior would have evolved in relative isolation, driven primarily by the increasing sunlight rather than by any influx of material from outside. The golden hue that developed would therefore be the product of the hexagon's own interior chemistry, responding to changing solar illumination, a chemical fingerprint of seasonal change, written across a polar atmosphere 4 times wider than Earth. Researchers also considered other possibilities. Changes in atmospheric circulation patterns, driven by seasonal heating, could alter the vertical distribution of clouds, changing which layers are most visible at the wavelengths. Cassini's cameras observe variations in the overall dynamics of the polar vortex could affect how material is transported within the hexagon's interior. The color change might not be driven by a single mechanism, but by the combined effect of several atmospheric processes, all responding simultaneously to the arrival of spring. The Cassini team initiated a formal investigation of the color change mechanism, but the mission ended before a definitive explanation could be established. The color change from blue to gold is confirmed. The precise mechanism that produced it is understood in outline through the seasonal photochemistry hypothesis, which is the current leading interpretation, but remains an area of ongoing scientific interest rather than a fully closed question. What the color change also demonstrated was something that the early years of hexagon research had perhaps underappreciated. The hexagon is not a static feature. It responds to Saturn's seasons. It changes on timescales that, while long by human standards 4 years for a color transformation, 7-year seasons, a 29-year year, are observable within the span of a single well-designed spacecraft mission. The hexagon has a life. It evolves. Its interior atmosphere is not frozen in a fixed state, but is dynamically responding to the energy environment of Saturn's changing orbital position. This seasonally dynamic character made the hexagon more interesting scientifically, because it meant that observations across multiple Saturn seasons could reveal how the feature responds to different solar illumination regimes, potentially illuminating the physics that creates and sustains it. But the color change was not the most structurally significant discovery that Cassini contributed to hexagon science. That distinction belongs to something that emerged, not from Cassini's cameras, but from its infrared spectrometer observations. At higher altitudes, a discovery that expanded the hexagon from a single atmospheric structure into something with a vertical dimension far greater than anyone had initially proposed. In Cassini data, analyzed by a team led by Lee Fletcher of the University of Leicester, researchers identified a second hexagonal structure not at the cloud level where the familiar hexagon resides, but in the stratosphere of Saturn, significantly higher in the atmosphere than the visible cloud tops. Saturn's stratosphere is the atmospheric layer above the clouds, where temperatures increase with altitude due to the absorption of solar ultraviolet radiation by atmospheric gases, rather than decreasing as they do in the lower atmosphere. This region sits far above the weather we can see in Saturn's visible light images, and it is a region that is considerably harder to observe. But Cassini's composite infrared spectrometer could probe atmospheric temperatures at multiple altitudes and in the temperature structure of Saturn's stratosphere. Fletcher's team identified a feature whose geometry matched the hexagon below a hexagonal temperature pattern in the stratosphere. Located above the cloud-level hexagon and sharing its six-sided geometric organization, this was a remarkable finding. A single hexagonal jet stream at a single atmospheric level is already an extraordinary feature. But a second hexagonal structure at a completely different altitude in the atmosphere, separated from the first by a substantial vertical gap, suggested that the hexagon's geometric influence was not confined to the layer of atmosphere where it is most visible. Something was imprinting a hexagonal pattern across multiple vertical levels of Saturn's atmosphere. The immediate question was whether these two hexagonal features were the same structure, physically connected throughout the intervening atmosphere, or whether they were separate features that happened to share a similar geometric form. The physics of atmospheric wave propagation provided a crucial clue, and the clue was initially problematic for the straightforward explanation. Atmospheric waves, the kinds of oscillations and patterns that can form in a stratified atmosphere, can, under some conditions, propagate vertically, traveling from lower atmospheric levels to higher ones, or vice versa. If the cloud-level hexagon were generating waves that propagated upward into the stratosphere, those waves could potentially imprint a hexagonal pattern at higher altitudes. This would be the simplest explanation for why both levels show hexagonal structure. But the atmospheric conditions at Saturn present a significant obstacle to simple vertical wave propagation. Between the cloud level and the stratosphere lies a region of the atmosphere where the wind speed changes dramatically with altitude, where there is substantial vertical wind shear. In atmospheric physics, there is a well-established principle governing when waves can propagate vertically through regions of wind shear. They can do so when conditions called waveguide conditions are satisfied, and they cannot when those conditions are not met. Analysis of the temperature and wind profiles between Saturn's cloud level and its stratosphere, derived from Cassini data, suggested that the conditions for straightforward vertical wave propagation between these two levels were not clearly satisfied. The wave from below should not easily reach the stratosphere, yet the hexagonal feature was there in the stratosphere. This created a puzzle within a puzzle. The stratospheric hexagon was confirmed. The mechanism that could connect it to the cloud-level hexagon was not clearly established. Several possibilities remained on the table. Perhaps the vertical wave propagation constraints were different from what simplified models suggested, and the waves did propagate upward through some mechanism that the analysis had not fully captured. Perhaps the stratospheric hexagon and the cloud-level hexagon were both manifestations of a much deeper feature that extended all the way from below the clouds through the stratosphere, a vertically coherent structure rooted deep in Saturn's atmosphere, whose signature appeared at both levels without requiring communication between them. Perhaps the stratospheric hexagon formed through a separate mechanism one that happened to produce the same six-sided geometry as the cloud-level feature, but was driven by different physics at higher altitudes. None of these possibilities could be decisively confirmed or ruled out by the Cassini data alone. The stratospheric hexagon remained an open question, confirmed as an observation, uncertain as to its physical connection to the feature below. Fletcher's team noted in their published work that the stratospheric findings suggested the hexagon's influence extended much higher in Saturn's atmosphere than previously appreciated, and that understanding the connection between the two levels would require future observations at higher resolution and across a wider range of Saturn's seasonal cycle than Cassini could provide. This was, in the language of the scientific literature, an invitation for future investigation. It was also, in the broader language of science communication, a hint that the hexagon was not the relatively bounded, single-layer feature that the first generation of observations had suggested. It had depth below the clouds. It had a presence above them. The full vertical extent of its influence was unknown, and that unknown became substantially more pressing and substantially more mysterious after the data from a November 2024 observation session by the James Webb Space Telescope began to be analyzed. But that story belongs to its own chapter. For now, within the Cassini era, the accumulating revelations about the hexagon's vertical structure had another implication that deserves attention. They constrained what kinds of physical explanations could be valid. A purely surface phenomenon, a pattern that existed only in a thin atmospheric layer, would not need to account for vertical coherence across multiple atmospheric levels. But a feature that appeared at the cloud tops, extended several hundred kilometers below them, and generated a matching geometric signal in the stratosphere above, needed a physical explanation that operated across the full atmospheric column, not just at a single level. The mechanism responsible for the hexagon had to be deep-rooted enough to organize the atmosphere at cloud level, coherent enough to extend that organization downward through increasing pressure, and influential enough to generate a corresponding signature at stratospheric altitudes through some mechanism, whether direct wave propagation, shared origin in a deeper feature, or some other dynamical connection that remained to be fully worked out. This accumulating picture of vertical extent made the hexagon more mechanistically demanding, not less. It was no longer sufficient to explain why a jet stream turned 6 corners at cloud level. The explanation also needed to address why that 6-sided organization propagated through the full atmospheric column in the way Cassini's data demonstrated. This was a harder problem, and it was a problem that the Cassini mission itself could only partially address, because the spacecraft was not designed to probe Saturn's deep atmosphere below the clouds, and the connection between the cloud level and stratospheric hexagons remained observationally under-resolved at the altitudes in between. The end of the Cassini mission itself was an extraordinary event, designed with both scientific and environmental considerations in mind. By 2017, Cassini had been at Saturn for 13 years. Its fuel was running low. The mission's planners had faced a choice: allow the spacecraft to eventually drift into an uncontrolled trajectory, risking contamination of one of Saturn's scientifically interesting moons, particularly Enceladus, where Cassini had confirmed the presence of a subsurface ocean and complex organic chemistry, or control its final trajectory deliberately. They chose the latter. On September 15, 2017, Cassini executed what the mission team called the grand finale. The spacecraft plunged into Saturn's atmosphere at high speed, transmitting data until the heat and pressure of atmospheric entry destroyed it. In its final moments, Cassini sampled the top of Saturn's atmosphere directly for the first time in the mission, a final scientific observation from a spacecraft that had transformed planetary science in 13 years of work. What Cassini's grand finale measured in those final seconds included atmospheric composition data from the top of Saturn's atmosphere that researchers are still analyzing years later. The in situ measurements of the upper atmosphere provided constraints on Saturn's internal structure and atmospheric chemistry that remote sensing could not achieve. And although the Hexagon was not the primary target of the grand finale plunge, Cassini entered at a location not directly above the Hexagon. The mission's final acts were part of a continuous observational legacy that included everything learned about the Hexagon over the full 13 years. With Cassini gone, the Hexagon returned to the status it had held before 2004, an object visible only through the limited resolution of Earth-based and Earth orbit-based telescopes, without a dedicated spacecraft to probe its details. Earth-based infrared telescope observations could confirm its presence and track major changes. The Hubble Space Telescope, now equipped with instruments far superior to those available during its early Hexagon observations, could image Saturn's polar regions with much greater clarity than the pre-Cassini Hubble observations. These resources allowed researchers to confirm that the Hexagon persisted after Cassini's departure. It had not been somehow dependent on the spacecraft's presence. As obvious as that sounds, stated plainly, and to track any large-scale evolution of the feature. But the Hexagon remained in many fundamental respects as mysterious as it had been before Cassini. The mission had confirmed its dimensions with extraordinary precision, mapped its internal structure, revealed the color change and the stratospheric analog, identified the barrier chemistry and the polar vortex characteristics, and generated a rich dataset that supported the development and refinement of physical models. None of this was trivial. The Cassini dataset was and continues to be a scientific resource of enormous value. But the fundamental question, why exactly does this structure form? And why does it maintain its geometric regularity with such exceptional stability over timescales of decades, remained contested among competing theoretical models. The mechanistic explanation for the Hexagon had been substantially narrowed and refined by Cassini's observations, but it had not been definitively resolved in the way that, for instance, Cassini's discovery of Enceladus's plumes had definitively resolved the question of whether that moon was geologically active. The theoretical landscape that Cassini's observations had helped to shape was complex and active. Researchers had developed and tested multiple physical explanations for the Hexagon, and the data had helped to discriminate among them, ruling out some mechanisms, supporting others, identifying specific observational tests that future data could perform. The most viable remaining explanations had been considerably refined by the Cassini era. But refinement is not resolution, and the Hexagon's physics, particularly the question of why 6 sides specifically, and why those sides were so geometrically stable, continued to resist the kind of single, universally accepted mechanistic explanation that would close the scientific book on the feature. Instead, what Cassini left behind was a feature understood in outline, supported by the richest observational dataset any atmospheric structure in the outer solar system had ever accumulated, but still containing open questions at its mechanistic core. The depth of the feature below the clouds, potentially much greater than the first estimates of 100 kilometers, with some researchers arguing for depths of thousands of kilometers into Saturn's interior, was not settled. The connection between the cloud-level hexagon and the stratospheric hexagon was not settled. The mechanism of the color change, while explained through the seasonal photochemistry hypothesis, was not fully characterized. The question of the South Pole's circular vortex versus the North Pole's hexagon, the hemispheric asymmetry, was not definitively resolved. And above all of these specific unresolved questions hovered the larger one. What, precisely, is the complete physical mechanism that creates a hexagonal standing wave in Saturn's jet stream, maintains it with such extraordinary geometric precision across decades of a turbulent, fluid, gas giant atmosphere, locks its rotation rate to Saturn's interior, rather than to the faster and variable winds of the visible atmosphere, and imprints its geometric signature across multiple vertical levels of the atmosphere, from deep below the clouds to high above them? That question, detailed in its mechanics, multiple in its aspects, is the question that the theoretical work of the Cassini era addressed with increasing sophistication, and the question whose answer we will begin to assemble in depth in the section that follows. But before arriving there, one final piece of the Cassini era story deserves attention, because it establishes something important about the hexagon's nature that often gets lost in the focus on its geometric shape and its extraordinary persistence. The hexagon is not merely a curiosity of Saturn's North Pole. It is a scientific model system, a phenomenon that, because it is extreme, geometrically distinctive, observable at high resolution, and long-lived, provides a test case for theories of atmospheric dynamics that have applications far beyond Saturn. The patterns that a rotating fluid produces under different conditions of rotation rate, jet stream width, jet stream speed, and surrounding pressure gradients are not unique to Saturn. They are governed by equations that apply wherever fluids rotate on any planet with an atmosphere, in any ocean with currents, in any star with convective flows. The hexagon exists at a particular set of parameter values: Saturn's rotation rate, jet stream properties, and atmospheric conditions that happen to produce a stable six-sided polygon. Different parameter values would produce different polygon counts, or no polygon at all. The question of why 6 sides specifically, and not 5 or 7, is a question about the precise value of those parameters and how they interact with the physics of jet stream instability. Understanding why Saturn's North Pole produces a hexagon, while its South Pole produces a circle, and why Jupiter's poles produce clusters of multiple smaller cyclones in geometric arrangements rather than single large polygons, requires understanding the same physical equations applied to different conditions. Each planetary atmosphere is a data point in a broader exploration of what rotating fluids can do. This is why the hexagon matters to planetary scientists studying distant worlds they have never visited and may never visit. The equations that produce Saturn's hexagon are the same equations that govern the atmospheric circulation of hot Jupiter exoplanets orbiting distant stars. They are the same equations relevant to the jet streams of gas giant exoplanets in other solar systems. Planets whose weather we cannot directly observe, but whose atmospheric behavior we want to understand through models. If we can fully explain Saturn's hexagon, if we can identify every physical mechanism that creates and sustains it with complete quantitative precision, we gain a validated model that can be applied to atmospheric conditions we cannot directly sample. Saturn's hexagon is, in this sense, not just a feature of one planet in our solar system. It is a window into the physics of planetary atmospheres in general. That ambition to use the hexagon as a template for understanding atmospheric organization beyond Saturn was already present in the scientific literature of the Cassini era. Researchers noted that polygonal vortex structures had been produced in laboratory experiments under conditions analogous to Saturn's, that mathematical studies had identified the parameter regimes in which stable polygons could form, and that the theoretical framework being developed to explain the hexagon could in principle be extrapolated to other planets given sufficient knowledge of their atmospheric properties. The hexagon was simultaneously a specific, local mystery to be solved and a general, universal phenomenon to be understood. That dual character, local mystery and universal template, is part of what has made the hexagon such a persistent focus of planetary science research, even in the years after Cassini's departure. And it is part of what made the James Webb Space Telescope's first extended look at Saturn's atmosphere so significant, because JWST did not just add another layer of observational detail to an already richly characterized feature. It revealed something that no instrument before it could have revealed, something that overturned assumptions about how vertically bounded the hexagon's influence was, and something that expanded the mystery of the hexagon to include atmospheric layers that previous research had not seriously considered as part of the hexagon story. The physics of how that expansion works and what it reveals about the hexagon's mechanism is the subject of what comes next. There is a moment in every scientific investigation when the question shifts. It starts as a what. What is that thing? What are its properties? What does it look like from every angle we can observe it from? And it becomes a why. Why does that thing exist? Why does it take the form it takes? Why do the rules of physics, applied to the specific conditions of this specific place, produce this specific outcome and not some other outcome? The why question is harder than the what question. The what question can be answered with better instruments and more observation time. The why question requires theory, requires building a model of the underlying mechanism, testing that model against the observations, refining it when it fails to match, and eventually arriving at an explanation that is not just consistent with what has been observed, but that makes specific, testable predictions about what has not yet been observed. The hexagon reached the why question decades ago, and the journey toward a satisfying answer has been as strange and demanding as the feature itself. Let us begin with what the early researchers had to work with, because the initial theoretical landscape around the hexagon was not empty. Planetary scientists in the 1980s and 1990s had frameworks for thinking about large-scale atmospheric waves on giant planets, and those frameworks provided a natural starting point for explaining a structure that, whatever else it was, clearly involved an organized pattern propagating through Saturn's atmosphere. The early favorite was a class of atmospheric oscillation called a Rossby wave. Rossby waves are real, well-understood phenomena. They are large-scale oscillations that occur in rotating fluids in the atmosphere and oceans of the Earth, and by extension in the atmospheres of any rotating planet. They arise because of the variation in the Coriolis effect with latitude. On a rotating planet, the component of the planet's rotation that is relevant to atmospheric dynamics changes as you move from the equator toward the poles. At the equator, the rotation axis is perpendicular to the local vertical, and the Coriolis effect has its minimum influence on horizontal motion. At the poles, the rotation axis aligns with the local vertical, and the Coriolis effect has its maximum influence. This variation in effective rotation, called the planetary vorticity gradient, provides a restoring force that sustains large-scale wave oscillations in the atmosphere. A parcel of air displaced poleward gains a relative negative vorticity compared to its surroundings. The restoring force pushes it back toward its original latitude, and the resulting oscillation propagates as a Rossby wave. On Earth, Rossby waves are responsible for the long meandering patterns of the upper-level jet streams, the large-scale troughs and ridges that weather forecasters track as they sweep eastward across the mid-latitudes. They are also responsible for blocking events, where the jet stream stalls and produces persistent regional weather patterns lasting for weeks. Applying this framework to Saturn's hexagon was a natural first step. A hexagonal standing wave could potentially be interpreted as a Rossby wave pattern that had become stationary, a wave oscillating at a particular frequency that matched the natural resonance of the atmosphere at that latitude, producing a pattern that did not propagate east or west, but instead stood fixed relative to Saturn's interior rotation. The six-sided shape could arise from a Rossby wave with a particular wave number, the number of complete wave cycles around the full latitude circle at 78 degrees north. A wave number of 6, meaning 6 complete oscillation cycles around the latitude circle, would produce exactly the 6 corners of the hexagon. This is an attractive explanation in outline. It invokes a well-understood physical mechanism, applies it in a straightforward way to Saturn's geometry, and produces the right number of sides as a consequence of the wave's spatial structure. And it was pursued seriously in the early theoretical literature on the hexagon. Researchers constructed Rossby wave models of Saturn's atmosphere and examined whether a stationary wave of wave number 6 could be generated and sustained under Saturn's atmospheric conditions. The difficulty was in the details. For a Rossby wave to be stationary, to stand in place rather than propagating, it needs to be in a very specific resonance condition with the background flow. The background winds at the latitude of the hexagon and the variation of the planetary vorticity gradient with latitude together determine what wave number can be stationary under those conditions. When researchers computed these parameters using the best available estimates of Saturn's atmospheric wind profile, the predictions did not match cleanly. The wave number required for stationarity, given Saturn's actual wind conditions, was not clearly 6. The fit was imperfect, and importantly, the Rossby wave model in its basic form did not naturally account for the extreme sharpness and geometric regularity of the hexagon's corners. Real Rossby waves on Earth produce gentle meanders with smooth curvature, not sharp angular turns. The hexagon's corners are distinctly pointed, not smoothly rounded. Any model that produced something resembling a hexagon in overall character but failed to reproduce the sharpness of its corners was missing something important. The Rossby wave hypothesis was not without defenders, and it stimulated valuable theoretical work on Saturn's atmospheric wave dynamics. But as the Cassini data accumulated and the hexagon's properties were characterized with increasing precision, the consensus among researchers studying the feature gradually moved away from simple Rossby wave models toward mechanisms that more naturally accounted for both the geometric regularity of the hexagon and the physical conditions at Saturn's North Pole. This shift was driven not by any single definitive experiment, but by the accumulating weight of evidence against the Rossby wave model's predictions and toward the predictions of alternative frameworks. The alternative that attracted the most sustained attention, and that represents the current leading mechanistic explanation for the hexagon, belongs to a different category of atmospheric dynamics: barotropic instability. The word barotropic refers to a specific type of atmospheric flow in which pressure varies only with density, a flow in which the density surfaces and pressure surfaces are aligned. In a barotropic atmosphere, the horizontal wind speed can vary with latitude. There can be strong jets, but the wind does not vary significantly with altitude. This is a simplification of real atmospheric conditions, but it is a useful one for capturing the dominant dynamics of large-scale atmospheric features in cases where the horizontal variation of the wind is more important than the vertical variation. Barotropic instability is what happens when a horizontal shear in the wind field, a region where wind speed changes rapidly with latitude, meaning air at one latitude is moving much faster than air at an adjacent latitude, becomes unstable and begins to develop oscillations. These oscillations grow in amplitude over time, extracting energy from the horizontal shear in the background wind. On Earth, barotropic instability contributes to the development of atmospheric disturbances in strong jet streams and to the formation of eddies along the boundaries between fast and slow-moving air masses. It is a well-understood mechanism with a substantial mathematical foundation in fluid dynamics theory. The key insight for the Hexagon is that Saturn's north polar atmosphere contains exactly the kind of horizontal wind shear that barotropic instability theory predicts should be unstable under certain conditions. The hexagonal jet stream sits at approximately 78 degrees north latitude. At this latitude, observations show a narrow band of high-speed eastward flow. The jet stream itself bordered on its poleward side by the polar vortex and on its equatorward side by slower-moving or differently directed flows. This velocity profile, with fast wind in a narrow band and slower flow on either side, is a horizontal shear structure. And horizontal shear structures in rotating fluids are susceptible to barotropic instability. The connection to the hexagon's shape comes from how barotropic instability develops in a rotating system. When a horizontally sheared jet stream becomes unstable, it does not simply collapse into turbulent chaos, at least not immediately. Instead, it develops organized oscillations at a characteristic spatial scale, determined by the width and speed of the jet and the rotation rate of the underlying planet. These oscillations have a specific wave number, a specific number of oscillation cycles that fit around the full latitude circle at the jet stream's location. The wave number that grows most rapidly from the instability is determined by the detailed properties of the flow. The critical insight, the one that makes barotropic instability a genuine candidate explanation rather than a generic atmospheric process, is that for Saturn's specific jet stream properties at 78 degrees north, the wave number that the instability theory predicts should dominate is wave number 6, exactly 6. The computation is not trivial, and it depends on specific assumed values for the jet stream width, speed, and background rotation rate. But when researchers plug in the values that Cassini's wind measurements provide for Saturn's north polar jet stream, the instability analysis consistently points toward a six-sided oscillation as the dominant unstable mode. The hexagon is not arbitrary. It is the mode that Saturn's specific atmospheric conditions select when a horizontal shear instability develops at this latitude. A jet stream with different width or different speed, or operating on a planet with a different rotation rate, would produce a different polygon or no polygon at all, just disorganized turbulence. This is a genuinely beautiful result. It means the hexagon is not a mystery of the same kind as a phenomenon for which no physical mechanism can even be proposed. It is a mystery of quantitative detail, of precisely characterizing the atmospheric conditions well enough to confirm that the instability analysis gives wave number 6 rather than 5 or 7. The mechanism exists, is understood in its theoretical framework, and applies to Saturn's North Pole in a way that the available observations support. The remaining scientific work is in confirming the precise parameter values that drive the instability to its six-sided solution, and in extending the analysis to account for the hexagon's extraordinary stability over time rather than its formation. Because that is a separate and in some ways more demanding question. Barotropic instability is a mechanism for generating an oscillation in a jet stream. It explains why the perturbation that starts the hexagon off growing would have a six-sided geometry. But a standard barotropic instability analysis produces a wave that grows and then, eventually, either saturates in some nonlinear state or disrupts the jet stream that generated it. What it does not automatically explain is why the hexagon has been stable for at least 40 years without either dissipating or changing its wave number. A wave number 6 oscillation that grew from instability in 1981 should, absent some sustaining mechanism, have evolved over the intervening decades. It has not, or at least, its fundamental geometric character has not changed in ways that any instrument has been able to detect. This longevity question pushed researchers toward the deep atmosphere. If the hexagon extends far below the visible cloud tops, not just 100 kilometers, but potentially thousands of kilometers into Saturn's interior, as some models suggest, then its mechanical footprint in the atmosphere is vastly larger than a shallow surface feature. A feature that is deeply rooted in the atmosphere is harder to disrupt than one that exists only near the surface. It has more inertia, more dynamical stability, more resistance to perturbations from above. The depth of the hexagon's roots may be what makes it so persistent. A shallow jet stream instability can be disrupted by turbulence, by seasonal changes in the temperature structure, by large-scale weather events. A feature that extends thousands of kilometers deep into a gas giant's interior is anchored by an atmospheric column of enormous mass and momentum, and disrupting it would require an energy input orders of magnitude larger than what Saturn's atmospheric weather can provide. The question of how deep the hexagon goes became one of the most actively pursued research questions in the post-Cassini literature. Cassini's instruments could probe several hundred kilometers below the visible cloud tops through the thermal emission of Saturn's internal heat, but they could not image the deep atmosphere directly. The Juno spacecraft, which has been in orbit around Jupiter since 2016, and whose instruments include a microwave radiometer capable of probing deep into Jupiter's atmosphere, demonstrated that some of Jupiter's large-scale weather features extend far deeper than visible light or near-infrared imaging could reveal, in some cases, thousands of kilometers deep. This result from Jupiter made the hypothesis of a deeply rooted Saturn hexagon more physically credible, even in the absence of direct measurements of Saturn's deep atmosphere. A mission capable of probing Saturn's deep atmosphere with the kind of microwave radiometry that Juno applied to Jupiter would provide crucial data for resolving the depth question. No such mission is currently in operation at Saturn, though mission concepts for returning to the Saturn system have been under development by NASA and ESA. The hexagon's depth, therefore, remains a constrained estimate rather than a directly measured quantity. The observational lower bound, the deepest level at which Cassini instruments directly detected hexagonal structure, is several hundred kilometers. The theoretical upper bound, the maximum depth, consistent with Saturn's interior structure and the stability of the feature, extends potentially to depths where the atmosphere transitions toward liquid hydrogen thousands of kilometers below the cloud tops. The true depth lies somewhere in this range, and determining it precisely is one of the highest priority scientific questions for a future Saturn mission. The stability of the hexagon over time also brought a separate theoretical contribution into the discussion, one that came from a completely different direction than the traditional atmospheric wave and instability models. In 2020, a team at the California Institute of Technology published a mathematical study that identified a mechanism by which a stable polygonal structure could form and persist in a rotating atmospheric system. The mechanism they described, anticyclonic shielding, works as follows. When a central cyclonic vortex, like Saturn's north polar vortex, is surrounded by a ring of winds rotating in the opposite direction, an anticyclonic ring, the anticyclonic winds act as a barrier. They isolate the central vortex from the surrounding atmosphere, preventing large-scale mixing and stabilizing the geometric shape of the boundary between the vortex interior and the exterior flow. Under specific conditions involving the relative sizes and speeds of the cyclonic vortex and the surrounding anticyclonic ring, the boundary between them does not form a smooth circle, but instead locks into a stable polygonal shape. The mathematics of this mechanism are elegant and physically transparent. The polygon forms because the anticyclonic ring's geometry creates a set of points around the vortex boundary, where the competing cyclonic and anticyclonic flows produce a standstill, where neither the inward pressure from the exterior flow nor the outward pressure from the vortex interior dominates. These standstill points correspond to the corners of the polygon. Between the corners, the jet stream can maintain a relatively straight path because the flow on both sides is roughly balanced. At the corners, the geometry forces a sharp turn. The result is a polygonal boundary whose number of sides is determined by the ratio of the cyclonic vortex size to the anticyclonic ring size, the same kind of wave number selection that appears in the barotropic instability analysis, but derived through a different mathematical route. The Caltech study did not claim to have definitively solved the hexagon mystery. It presented anticyclonic shielding as a mechanism that could in principle produce and maintain a stable polygon, and it showed mathematically that this mechanism was consistent with producing a six-sided polygon under conditions plausibly analogous to Saturn's North Pole. It was a theoretical candidate, supported by rigorous mathematics, but not yet confirmed by direct observational test. Researchers working on Saturn's hexagon received it as an important and potentially complementary contribution to the barotropic instability framework, a mechanism that might explain the hexagon's persistence and stability. Even after the initial instability had generated the six-sided form, the instability creates the hexagon, the anticyclonic shielding sustains it. These are not mutually exclusive ideas. They may be successive stages of the same physical process. There is a third line of evidence for the hexagon's physics that comes not from mathematical theory or spacecraft observation, but from the laboratory, from experiments designed to physically reproduce the conditions that generate polygonal vortex patterns in rotating fluids. These experiments are among the most direct demonstrations available that the hexagon's geometry is a genuine consequence of fluid dynamics in rotating systems, and not some exotic phenomenon specific to Saturn's unique atmospheric composition or history. The most influential laboratory demonstrations have involved rotating cylinders or tanks of fluid, with different parts of the fluid driven to rotate at different speeds. In the simplest version of these experiments, a cylindrical container of water is placed on a rotating turntable. The fluid in the outer part of the cylinder rotates with the turntable at one speed. A central cylinder or some other mechanism at the center is driven to rotate at a different speed, creating a difference in rotation rate between the inner and outer regions of the fluid. This differential rotation generates a shear layer, a region where the flow speed changes rapidly with radial distance, analogous to the horizontal shear at the edge of Saturn's polar jet stream. Under the right conditions, the right differential rotation rate, the right fluid viscosity, the right geometry of the container, the shear layer in these rotating fluid experiments does not remain featureless. It becomes unstable, and the instability organizes the flow into a polygonal pattern. Hexagons appear, pentagons appear, triangles appear. The specific polygon that emerges depends on the parameter values of the experiment, particularly the ratio of the inner and outer rotation rates. Adjusting these parameters systematically moves the system from one polygon to another, confirming that the wave number is not fixed but is selected by the specific conditions of the flow. When the parameters are set to values that correspond, in the appropriate analogy, to Saturn's North Polar jet stream geometry, the experiments consistently produce hexagons. When the parameters are adjusted in ways that correspond to changing the latitude of the jet stream, or to different planetary rotation rates, or to different jet stream widths, different polygons emerge. These laboratory results are powerful in a specific scientific sense. They demonstrate that no exotic physics is required to produce a hexagonal vortex. Plain water, a rotating container, and a differential rotation rate are sufficient. The same physical equations that govern water in a laboratory tank govern the gas in Saturn's atmosphere. Scale is different. Composition is different. The absolute values of forces and velocities are wildly different, but the fundamental dynamics, the mathematics of a rotating shear layer becoming unstable and locking into a polygonal mode are the same. The laboratory hexagons are physically smaller than a single cloud feature inside Saturn's polar vortex, but they are mechanistically identical. They are proof of concept at human scale that the mechanism responsible for Saturn's hexagon is real, reproducible, and governed by well-understood physics. This connection between the laboratory and the planet is one of the most satisfying aspects of hexagon science. It means that the mechanism is not merely hypothesized but physically demonstrated. Researchers can build the relevant conditions in a tank of water on a laboratory bench, photograph the resulting hexagonal flow pattern, and say with confidence, "This is the same thing that is happening at Saturn's North Pole, at 10 billion times the scale." That scale difference is enormous, obviously. And there are complications. In applying the laboratory results directly to Saturn, Saturn's atmosphere is stratified in ways that a tank of water is not. It has internal heat sources. It has a composition gradient. With altitude, its jet stream is influenced by features above and below it that a simple laboratory tank cannot capture. These complications matter for quantitative precision. They do not undermine the fundamental demonstration that the mechanism itself is physically real. One specific detail from the laboratory experiments deserves particular attention because it directly addresses one of the hexagon's most puzzling properties, its failure to drift in longitude. In Saturn's atmosphere, most visible cloud features drift. The banded cloud structure at lower latitudes shows different drift rates at different latitudes, reflecting the differential rotation of Saturn's atmosphere. Features in faster wind bands drift more quickly in the direction of rotation. Features in slower bands drift more slowly. This differential drift has been used to measure wind speeds across Saturn's disk by tracking how quickly individual cloud features move relative to a reference frame set by Saturn's interior rotation rate. The hexagon does not drift this way. Its rotation rate matches Saturn's interior rotation rate, not the wind speed of the atmosphere at its latitude. The visible atmosphere at 78 degrees north moves faster than the hexagon pattern rotates. This means the atmospheric gas at the hexagon's latitude is moving through the hexagonal pattern, not with it. Individual parcels of gas enter the hexagon's jet stream, travel along one side, turn at a corner, travel along the next side, and eventually exit the hexagon's flow, while the hexagonal pattern itself, the wave, the oscillation, the standing geometric form, remains stationary relative to Saturn's interior. This distinction between the motion of the material and the motion of the pattern is a fundamental concept in wave physics. On Earth, a familiar analogy is a wave on the surface of water. When you watch waves crossing a lake, the surface of the water moves up and down, but the water itself does not travel horizontally in the direction the waves are moving. The pattern the wave crest moves across the surface. The water molecules move vertically. The hexagon is a much more complex version of the same conceptual distinction. The gas that makes up the jet stream is moving at 320 kilometers per hour in the direction of Saturn's rotation. The hexagonal pattern that this jet stream describes is rotating much more slowly, synchronized to the planet's interior rather than to the atmospheric winds. This synchronization with the interior is a crucial constraint on the hexagon's physical origin. If the hexagon was simply an instability pattern generated spontaneously in the visible atmosphere with no connection to what lies beneath, it would be expected to rotate at a rate determined by the visible atmospheric winds or some weighted average of atmospheric winds at different levels. It would not be expected to lock precisely to Saturn's interior rotation rate. The fact that it does lock to the interior rate suggests that the hexagon is not a self-contained atmospheric phenomenon. It is dynamically connected to something deeper, to the rotation of the layers below the clouds, possibly including the deep atmosphere of liquid hydrogen where the interior rotation rate is defined. The hexagon is a surface expression of deep atmospheric dynamics, not a skin-deep pattern painted on the upper atmosphere. This connection to the interior is one of the reasons why the question of the hexagon's depth is so scientifically important. If the hexagon extends thousands of kilometers into Saturn's interior, its rotation rate would be set primarily by the deep layers rather than the shallow ones. The hexagonal pattern at the cloud tops would be the visible tip of a structure rooted in conditions far below anything we can directly observe. The fact that the hexagon's period matches Saturn's internal rotation rate, the same rate inferred from Saturn's radio emissions, which are generated in the deep interior, is consistent with this interpretation. The hexagon's clockwork rotation may be the signature of its deep roots, visible at the surface because the hexagonal wave extends all the way up from those depths. These are the physical ingredients that the best current models of the hexagon incorporate: barotropic instability, selecting a wave number 6 oscillation from Saturn's north polar jet stream, anticyclonic shielding potentially sustaining the resulting polygon over long timescales, and a deep vertical extent that anchors the feature to Saturn's interior rotation and provides the dynamical stability needed for persistence across decades. No single model captures all of these elements in a fully self-consistent way, with quantitative parameter values confirmed by direct measurement. The theoretical picture is a framework, a set of physical mechanisms that individually have strong support and that collectively provide a plausible account of the hexagon's properties. But it is not yet the kind of single, complete, precisely parameterized physical model that would constitute a full solution. The hexagon is understood in principle. It is not yet fully characterized in quantitative detail. What makes this theoretical incompleteness interesting rather than merely frustrating is that it is scientifically productive. An incompletely understood phenomenon generates specific, tractable questions that can be addressed by better data. The hexagon's remaining mysteries are not open-ended puzzles with no clear path toward resolution. They are constrained by what is already known, and the constraints point towards specific types of observations: deep atmosphere probing by a future Saturn mission, high-resolution mapping of the jet stream velocity profile at multiple atmospheric levels, long baseline monitoring of the hexagon's properties across a full Saturn season that could resolve the outstanding questions. The hexagon is a scientific problem in the most useful sense. Hard enough to be interesting, constrained enough to be solvable. There is another dimension to the hexagon's physical story that has not yet been fully engaged, and it concerns not the mechanism of the hexagon itself, but the specific property of Saturn's atmosphere that makes the hexagonal solution possible at all. Consider again the question of why the South Pole has a circular vortex instead of a hexagon. Both poles experience Saturn's planetary rotation. Both poles have atmospheric dynamics driven by the same internal heat source. Both poles have the same overall atmospheric composition, yet one has a hexagon and one has a circle. The hemispheric asymmetry is real and confirmed, and explaining it requires identifying what is physically different between Saturn's north and south polar atmospheric environments. One candidate difference is seasonal state. At any given moment in Saturn's long year, the north and south poles are in different seasons. One is in summer, the other in winter, with the transition driven by Saturn's orbital position. During the Voyager observations of the 1980s, and during the early Cassini observations of the 2000s, Saturn's north pole was in winter, while the south pole was in summer. A polar atmosphere in winter receives no sunlight, which changes the temperature structure of the upper atmosphere through the absence of solar heating. A polar atmosphere in summer receives continuous sunlight, which warms the stratosphere through photochemical absorption. These temperature structure differences affect the stability properties of the atmosphere and the propagation characteristics of atmospheric waves. It is possible that the difference between a hexagonal North Pole and a circular South Pole during the Voyager and early Cassini era was in part a seasonal effect, that the northern winter atmospheric structure favored the hexagonal instability mode, while the southern summer structure did not. This hypothesis predicts that as Saturn moves through its year and the hemispheres exchange their seasonal states, the atmospheric dynamics at the two poles should also change. As the northern hemisphere passed through its equinox in 2009 and began its spring and summer, the temperature structure of the north polar atmosphere was changing in ways that might affect the hexagon's properties. Cassini observed these changes. They include, among other things, the color change from blue to gold, but it did not observe the hexagon disappearing or changing its wave number over the seasonal transition it monitored. The hexagon persisted through the seasonal change, which suggests that if seasonal state affects the hexagonal instability, the effect is not strong enough to dissolve the hexagon during a seasonal transition. The hexagon is robust. Whether a hexagon also develops at Saturn's south pole as that hemisphere moves into its winter, as it is doing in the decades following the Cassini mission, is a question that current observations cannot definitively answer. Earth-based and Hubble observations of Saturn's south pole have not clearly detected a hexagonal structure there, but the resolution and observation time available to these instruments are insufficient to rule one out. A dedicated spacecraft at Saturn could address this question definitively, and doing so would provide an extremely valuable test of the seasonal hypothesis and of the broader theory of the hexagon's origin. The physical story of the hexagon, from Rossby wave hypotheses to barotropic instability to anticyclonic shielding to deep atmospheric roots to the question of hemispheric asymmetry, is a story of science working as it should. Each layer of explanation is driven by evidence, each theory is constrained by observation, and each answer generates new questions that are themselves scientifically productive. And the theoretical framework that has been assembled from this process is not merely an explanation of Saturn's hexagon. It is a set of physical tools that applies wherever rotating fluids develop horizontal shears, wherever a jet stream forms in a planetary atmosphere, wherever a current shear layer develops in a planetary ocean, wherever angular momentum differences in a stellar convection zone generate organized flow patterns at a boundary. The hexagon's physics is universal physics, encountered most clearly and most visually at Saturn's north pole, but operating wherever the relevant conditions are met. That universality is what makes the next chapter of this story so significant, because when the James Webb Space Telescope turned its instruments on Saturn in November of 2024 and found structures in the upper atmosphere that nobody had predicted and that nobody can currently explain, it was not just expanding the mystery of one planet's weather. It was demonstrating that the physical systems governing planetary atmospheres are connected across altitudes, across atmospheric layers, and potentially across the boundary between a planet's weather and its magnetosphere, in ways that our theoretical frameworks have not yet fully incorporated. The hexagon, it turns out, is merely the most visible piece of something that extends far beyond it, and discovering how far is the challenge that now defines the frontier of Saturn science. On the 29th of November 2024, the James Webb Space Telescope stopped looking at distant galaxies and turned towards something much closer. The telescope trained its instruments on Saturn and observed it continuously for 10 hours. 10 hours is not a long observation window by the standards of long baseline astronomy, but on Saturn, it corresponds to roughly one complete rotation of the planet, long enough to track how atmospheric features move across the disk, long enough to follow the hexagon through a full cycle of its geometry, long enough for JWST's unprecedented infrared sensitivity to capture something that no instrument before it could have seen in Saturn's atmosphere at these altitudes. The team conducting this observation was an international collaboration of 23 scientists from institutions in the United Kingdom, the United States, and France, led by Professor Tom Stallard of Northumbria University. They were not primarily hunting for the hexagon. They were hunting for atmospheric chemistry in Saturn's upper atmosphere, the region above the cloud deck, well into the stratosphere and ionosphere, using two specific molecular tracers to probe different altitude ranges simultaneously. The first tracer was hydrogen-3 ions, written by chemists as H3+. This is a positively charged form of the hydrogen molecule, 3 hydrogen atoms sharing 2 electrons, carrying a net positive charge, produced in Saturn's upper atmosphere through a series of reactions driven by the ultraviolet radiation and energetic particles that flow into the planet's polar regions along magnetic field lines from the solar wind. Hydrogen 3+ plays a significant role in the chemistry of Saturn's ionosphere, participating in reactions that influence both the composition and the energy balance of the uppermost atmospheric layers. It also emits infrared radiation at characteristic wavelengths that can be detected by a sufficiently sensitive infrared spectrometer. JWST's near-infrared spectrograph is that spectrometer. It can detect hydrogen 3+ emission from Saturn's ionosphere from altitudes of approximately 1,100 kilometers above Saturn's nominal surface, using the 1 bar pressure level as the reference, with a sensitivity that no ground-based telescope or previous space telescope has matched. The second tracer was methane. Saturn's atmosphere contains methane throughout its depth, but the methane detectable at stratospheric altitudes, approximately 600 kilometers above the nominal surface, provides different information than the hydrogen 3+ in the ionosphere. By simultaneously observing both tracers across the full spatial extent of Saturn's polar region, the JWST team could in principle map the atmospheric structure and chemistry at 2 different altitude levels during the same 10-hour observation window, building a 3-dimensional picture of the upper atmosphere during a single sustained observation campaign. What they expected to find was something interesting, but bounded a better resolved picture of Saturn's auroral structures in the ionosphere, perhaps some evidence of atmospheric variability linked to the solar wind input, and a useful baseline measurement of stratospheric methane distribution for comparison with future observations. What they actually found exceeded every reasonable prior expectation in ways that the research team described, in the understated language of peer-reviewed science, as completely unexpected and completely unexplained. In the ionosphere, at the altitude where hydrogen 3+ emission was strongest, the JWST data revealed a chain of dark, bead-like patches embedded in Saturn's auroral emission. These features were concentrated in the polar region, distributed around the pole in a pattern that drifted slightly only a few degrees over the course of the 10-hour observation window. They were not single isolated spots, but a chain, a sequence of dark regions embedded in an otherwise bright auroral halo. The beads were stable for the duration of the observation, which is itself significant. A transient or rapidly evolving atmospheric feature might appear in one image and be gone in the next. These features were present throughout the full 10 hours, suggesting they were not brief fluctuations but sustained structures of some kind. Their exact size is constrained by JWST's resolution at Saturn's distance, but they correspond to spatial scales of hundreds to potentially a few thousand kilometers in Saturn's ionosphere. The word dark here requires some unpacking. The hydrogen 3+ emission in Saturn's ionosphere is brightest in the auroral regions, the areas where energetic particles from the solar wind are channeled along Saturn's magnetic field lines into the upper atmosphere, depositing energy that drives chemical reactions and excites the hydrogen molecules into emission. In the image of this emission, as JWST recorded it, the bright auroral bands form a characteristic pattern around the poles. The dark beads are regions within this bright emission where the signal is locally reduced, where the hydrogen 3+ emission is anomalously weak compared to its surroundings. They looked like holes or gaps in the auroral light. What could produce dark regions in auroral emission? Several mechanisms are physically conceivable. A local reduction in the influx of energetic particles from the magnetosphere into a specific region could reduce the production rate of hydrogen 3+, and therefore reduce emission at that location. This could happen if the magnetic field geometry in those regions deflected particles away rather than funneling them in. Local chemical reactions that remove hydrogen 3+ at an elevated rate could also reduce emission in specific regions. Or local variations in the temperature of the ionosphere could affect the emission intensity, since hydrogen 3+ emission strength depends on both the abundance of the ion and the local temperature. Each of these mechanisms is physically real in principle. None of them, as of the time the findings were presented, had been identified as the specific mechanism responsible for the observed dark beads. The research team offered the hypothesis that the features might result from complex interactions between Saturn's magnetosphere and its rotating atmosphere, potentially providing insights into the energy exchange processes that drive Saturn's aurora. But they were explicit that this was a hypothesis, not a conclusion. The dark beads are confirmed. Their cause is not. What made the ionospheric dark beads even more provocative was the relationship the research team identified between their location and a separate, simultaneously observed feature at a lower altitude. In the stratosphere, at approximately 600 kilometers above Saturn's nominal surface, 500 kilometers below the ionospheric beads, the JWST methane observations revealed an asymmetric, star-shaped structure emanating from Saturn's north pole. 4 of the 6 expected arms of this star pattern were clearly visible in the data, extending from the pole outward toward lower latitudes. The arms were not equal in brightness or width, hence the description of the structure as asymmetric, and their spatial organization was distinctly non-circular. They radiated from the pole in specific directions, not uniformly distributed around the polar axis. When the research team mapped the positions of the star pattern's arms onto Saturn's polar coordinate system and compared them to the geometry of the cloud-level hexagon below, they found something that stopped them. The arms of the star-shaped stratospheric structure appeared to emanate from positions directly above the corners of the hexagonal storm. 6 corners of the hexagon, 6 expected arms of the star pattern. 4 of the 6 visible, the other 2 presumably present, but below the detection threshold of this particular observation. The alignment was not approximate. The arms mapped onto the hexagon's corners with a precision that the team described as strikingly consistent. This alignment is the discovery that changes everything about how we think about the hexagon's vertical reach, because the corners of the hexagon are at cloud level. They are approximately 600 kilometers below the stratospheric star pattern and approximately 1,100 kilometers below the ionospheric dark beads. If the star pattern's arms are genuinely aligned above the hexagon's corners, and the JWST data suggests they are, then something about the geometry of the hexagon is being communicated upward through the entire atmospheric column, from the cloud deck through the stratosphere and into the ionosphere. The hexagon is not confined to its cloud-level home. Its geometric influence, in some form not yet understood, reaches through hundreds and potentially thousands of kilometers of atmosphere to leave its signature in the uppermost layers. Consider the vertical architecture of what JWST has revealed. At the bottom, at cloud level, sits the hexagonal jet stream, the structure that Voyager glimpsed in 1981, that Cassini documented in extraordinary detail across 13 years, that laboratory experiments reproduced in miniature on rotating tables. Above that, in the stratosphere, at an altitude of approximately 600 kilometers, sits the asymmetric star pattern with arms aligned above the hexagon's corners, a structure that Cassini's instruments could not resolve, but whose presence is now revealed by JWST's superior sensitivity. Above that, in the ionosphere, at approximately 1,100 kilometers altitude, sit the dark beads embedded in Saturn's aurora, with the darkest beads appearing to align, though the team cautioned this alignment might be coincidental with the strongest arm of the stratospheric star. From cloud deck to ionosphere, spanning the full vertical extent of Saturn's upper atmosphere, the hexagon's geometric signature may be present at every level. If this interpretation is correct, and the research team was appropriately cautious in how firmly they asserted it, given that the data are from a single 10-hour observation window, and the features require significantly more study before their nature can be established, then the hexagon is not a feature of Saturn's weather. It is a feature of Saturn's entire atmosphere, from the dynamic cloud-level jet stream, through the chemically complex stratosphere, to the auroral ionosphere, where Saturn's magnetic field and the solar wind interact. The hexagon is a building-spanning architectural element, not a single floor detail. Its roots may go deep into the planet. Its crown apparently touches the edge of space. This interpretation also raises an immediate and profound question. What physical mechanism could communicate the hexagon's six-sided geometry across 500 kilometers of stratosphere to produce a star pattern aligned with the corners? The stratospheric hexagonal feature, identified in Cassini data, the one discussed in Part 2, whose vertical propagation was already theoretically problematic, was at a lower altitude than the JWST stratospheric star pattern. Cassini's stratospheric hexagon was closer to the cloud level. The JWST star pattern sits higher still, and the ionospheric dark beads are higher yet. Each additional altitude at which the hexagon's geometric influence appears makes the vertical propagation problem more acute, because the intermediate atmospheric layers between each altitude have their own wind shear, their own temperature gradients, their own wave propagation characteristics that theoretical models must account for. One possibility is that the connection between levels is not through direct vertical wave propagation in the classical sense. Perhaps the mechanism is electromagnetic rather than mechanical. Saturn has a strong magnetic field, generated by electrical currents in its interior. The field, let's see, magnetic field, thread through the entire atmosphere, connecting the deep interior where the field is generated to the ionosphere, where charged particles flow along the field lines from the magnetosphere. If the hexagon's geometry, at cloud level, creates a systematic pattern in the electrical properties of the atmosphere, in the distribution of electric currents, or in the way charged atmospheric particles interact with the fast magnetic field, that pattern could, in principle, be communicated along magnetic field lines to the ionosphere without requiring mechanical wave propagation through the intervening atmosphere. The dark beads in the ionosphere, if they reflect a local suppression of energetic particle input from the magnetosphere, could represent exactly this kind of magnetically mediated influence. The hexagon's corners, through some chain of electromagnetic effects not yet worked out, deflecting the flow of magnetospheric particles in ways that produce dark patches in the auroral emission at specific locations. This is speculative. It is the kind of speculative reasoning that researchers engage in when they encounter a genuinely new observation and need to construct candidate explanations before any of them can be tested. The JWST team explicitly noted that their current explanations for both the dark beads and the star pattern are preliminary hypotheses awaiting confirmation. But the electromagnetic hypothesis is not arbitrary speculation. It draws on established physics of magnetosphere-atmosphere coupling that has been studied extensively in the context of Earth's aurora, Jupiter's aurora system, and Saturn's own previously known auroral structures. Applying this framework to the hexagon's influence on the ionosphere is a natural extension of existing knowledge. Whether it is the correct extension cannot be determined without further observations. The star pattern in the stratosphere is somewhat different in character from the ionospheric dark beads, and its alignment with the hexagon's corners may operate through a different mechanism. In a stratified atmosphere, a large-scale forcing at one altitude can generate atmospheric waves that propagate upward. If the hexagon's corners are sites of concentrated mechanical forcing regions where the jet stream's sharp turns generate intense local turbulence, atmospheric waves, and vertical momentum fluxes, then those corners could act as point sources of upward propagating wave energy. Waves generated at the hexagon's corners would propagate upward through the stratosphere, and where they were absorbed or refracted, they could deposit energy and momentum in the stratospheric air, creating temperature anomalies and circulation patterns aligned with the original corner locations. A star-shaped pattern with arms above the hexagon's corners could be the stratospheric expression of wave energy radiated upward from those corners. This mechanism, corner-generated wave propagation into the stratosphere, is physically plausible and does not require solving the problem of global vertical wave propagation that made connecting the cloud level and stratospheric hexagons difficult in the first place. It requires only local wave generation at the corners and upward propagation from those specific points, not a global coherent wave that preserves the hexagonal geometry through the full vertical extent of the atmosphere. The result would not look like a hexagon in the stratosphere. It would look like a star pattern with arms above each corner, which is exactly what JWST observed. These candidate mechanisms, electromagnetic communication along magnetic field lines for the ionospheric dark beads, local wave generation at the hexagon's corners for the stratospheric star pattern, are the kinds of hypotheses that future observations could test. A second extended JWST observation of Saturn's polar atmosphere, ideally at a different point in Saturn's seasonal cycle and covering a full planetary rotation, could determine whether the dark beads and the star pattern are persistent features or whether they vary on short time scales. If they are persistent, they constrain the mechanism to one that operates continuously rather than sporadically. If they vary, the nature of their variation, whether it correlates with solar wind activity, with Saturn's rotational phase, or with some other measurable property, could point toward the responsible physics. The research team behind the JWST observations has indicated that follow-up observations are planned. The question of what these features are and what they reveal about the hexagon's vertical influence is now an active research priority. The fact that JWST can detect them at all, given that Saturn's upper atmosphere produces extremely weak emissions, as Professor Stallard noted in the announcement of the findings, speaks to the telescope's extraordinary sensitivity in the infrared. Earlier telescopes and spacecraft instruments simply did not have the signal-to-noise ratio to detect features of this magnitude at these altitudes. The dark beads and the star pattern were always there. Presumably, we simply had no instrument capable of seeing them until JWST pointed its mirror at Saturn in late 2024. This is one of the recurring themes in the history of astronomy. Features that seem to emerge from nowhere when a new instrument becomes available were always present, awaiting the technology needed to reveal them. Saturn's rings were invisible to naked eye observation of ancient astronomers, not because they did not exist, but because human vision lacks the angular resolution to resolve them at Saturn's distance. The hexagon was invisible to telescopic observation before Voyager, not because it had just formed, but because no telescope could image Saturn's polar regions at the resolution needed to reveal it. The stratospheric hexagon in Cassini data was not discovered until researchers specifically analyzed the thermal infrared data with that question in mind. And the ionospheric dark beads and stratospheric star pattern lay hidden until JWST provided an instrument sensitive enough to extract their signal from the extremely faint emission of Saturn's upper atmosphere. Each of these discoveries followed the same pattern. A technological threshold crossed, a new window opened, and a feature revealed that expanded the scope of what the hexagon is and how far its influence extends. The progression from Voyager's first grainy glimpse to Cassini's rich multi-year characterization to JWST's unexpected revelation of upper atmospheric structures is a progression in which each step revealed not just more detail about the previously known picture, but a fundamentally larger picture. Voyager showed that the hexagon existed. Cassini showed that it was a layered, seasonally active, chemically significant system extending hundreds of kilometers below the clouds and into the stratosphere above. JWST has now shown that its influence may extend all the way to the ionosphere, 1,100 kilometers above the cloud tops, in patterns aligned with its corners that nobody anticipated and nobody can yet explain. The scale of this revelation deserves to be appreciated in full. 1,100 kilometers. That is the altitude of the JWST dark beads above Saturn's nominal surface. For comparison, the International Space Station orbits Earth at approximately 400 kilometers. The beads detected by JWST in Saturn's ionosphere are at an altitude more than twice the orbital distance of humanity's permanent off-world habitation. Between the cloud-level hexagon and these ionospheric features lies a vertical distance greater than the width of Earth's entire lower atmosphere multiplied many times over. And across that entire distance, through the cloud layer, through the clear troposphere above, through the stratosphere, through the mesosphere, and into the ionosphere, the hexagon's geometric signature appears to be present. If the hexagon is indeed imprinting its geometry on Saturn's ionosphere through whatever mechanism connects the cloud-level corners to the dark beads above them, then the hexagon is not just a weather feature. It is a coupling feature, a structure that links Saturn's deep atmosphere to its magnetic environment, that bridges the gap between the tropospheric weather domain and the magnetospheric particle domain. Such coupling features exist in other planetary systems. Earth's polar vortex influences stratospheric ozone chemistry. Jupiter's auroral features are shaped by the dynamics of the magnetosphere-ionosphere system. But a tropospheric weather feature appearing to geometrically organize structures in the ionosphere is not something that has been clearly documented anywhere else in the solar system. If JWST has revealed exactly this at Saturn, It represents a discovery category, a class of phenomena that is new to planetary science. The implications for how we think about planetary atmospheres are not small. The standard framework in atmospheric science divides the atmosphere into relatively distinct dynamical regimes, separated by altitude. The troposphere is where weather happens, driven by solar heating, planetary rotation, and in Saturn's case, internal heat. The stratosphere above it is chemically distinct, driven by different heating mechanisms, and not directly connected to the weather below except through specific wave propagation channels. The ionosphere above that is a plasma environment, driven primarily by the interaction between the planet's magnetic field and the solar wind, with limited mechanical connection to the neutral atmosphere below. These are useful categories, and the physical processes within each regime are genuinely different, but they are not airtight compartments. Coupling between regimes exists and is increasingly recognized as important. What the JWST findings suggest, if they are confirmed by further observations, is that the hexagon is a coupling feature of extraordinary vertical reach, one that organizes atmospheric structures across all three of these conventional regimes simultaneously. A feature whose corners in the troposphere generate star-shaped patterns in the stratosphere and dark beads in the ionosphere would be a vertically integrated atmospheric structure of a kind that requires a new category of description. Not weather, not aurora, something that connects them. A feature that bridges the full vertical extent of an atmosphere from the weather layer to the edge of space. This framing the hexagon as an atmospheric coupling structure rather than just a weather anomaly is not yet established science. It is the interpretation that the JWST data suggests, pending confirmation by further observations and development of theoretical models capable of reproducing what JWST saw. The research team was appropriately circumspect in how far they pushed this interpretation in their publication and in the public presentation of their findings at the EPSC-DPS 2025 joint meeting in Helsinki. Science proceeds carefully when evidence is new and mechanisms are uncharacterized. But the direction of the evidence is clear, and the direction points toward a hexagon that is far larger, in every spatial dimension, than the feature that Voyager first glimpsed and that has been studied ever since. Now, sit with that for a moment, because this is where the philosophical weight of the hexagon story comes fully to rest, and it rests in a place that is the opposite of comfortable in the best possible way. We have been watching this hexagon for over 40 years. We found it by accident in archive spacecraft data, years after it was recorded. We spent 2 decades unable to observe it directly because our instruments were not good enough. We sent a flagship spacecraft to Saturn for 13 years, specifically to understand it and the system it sits in, and we learned an extraordinary amount. We developed theoretical models that explain how it forms, how it sustains itself, why it has 6 sides rather than 5 or 7, why it locks to Saturn's interior rotation rather than drifting with the atmospheric winds, how it acts as a chemical barrier between its polar interior and the surrounding atmosphere, why it changed color with Saturn's seasons. And then we pointed the most powerful telescope ever built at it for 10 hours, and it told us that everything we had learned was correct and also insufficient. The features JWST found above the hexagon, the dark beads in the ionosphere, the star pattern in the stratosphere, are not the kind of discovery that overwrites what Cassini found. They are the kind of discovery that reveals that what Cassini found was a chapter of a longer story rather than the complete story. The Cassini-era hexagon is still everything Cassini showed it to be. And it is now also the organizing principle for atmospheric structures at altitudes that Cassini could not probe with the necessary sensitivity. The hexagon is deeper and taller than we knew. It spans more of Saturn's atmosphere than we had confirmed. And the mechanism by which its six-sided geometry is communicated upward through the atmospheric column, through the stratosphere, into the ionosphere, potentially connecting to the magnetic field that threads through the entire planet, is a mechanism we do not yet understand. This is the condition that the hexagon leaves us in at the frontier of current knowledge, understanding more and knowing less than we did in 2017, the year Cassini went silent. Understanding more because the Cassini dataset is still being analyzed, because the theoretical models have been substantially refined in the years since, because the JWST data has added a new altitude range to the observational picture. Knowing less, because every new layer revealed by JWST has expanded the scope of what needs to be explained. The hexagon has grown with every observation campaign. It has never shrunk. This is a pattern worth pausing on, because it is not unique to the hexagon, but the hexagon illustrates it with unusual clarity. The universe does not reward scientific progress by revealing simpler and smaller phenomena as better instruments are deployed. It rewards scientific progress by revealing more complex and larger phenomena, by showing that what seemed to be a bounded feature has connections to things far beyond its apparent edges. The deeper you look at any aspect of the physical world with genuinely new tools, the more you find that it is woven into more of the rest of the world than you had appreciated. This is not a discouraging observation. It is the most accurate description of what science actually is, a process of discovering how connected everything is to everything else, of finding that boundaries drawn at the limits of previous instruments do not correspond to boundaries in nature. The hexagon is woven into Saturn's atmosphere, from its deep interior to the edge of space. We do not know how far down its roots extend. We do not fully know how high its influence reaches. We do not know what mechanism allows a tropospheric jet stream to organize the ionosphere above it. We do not know what the dark beads are. We do not know what drives the asymmetry of the stratospheric star pattern. And we do not know whether the hexagon is telling us something about Saturn specifically, or whether it is telling us something about the general principles of how large-scale atmospheric structures in rotating planetary systems couple to the plasma environments surrounding them, principles that would apply to every giant planet, every exoplanet with a magnetosphere and a dynamic atmosphere, every world in every solar system where gas and rotation and magnetic fields interact. What we do know is that Saturn's hexagon has been one of the most scientifically productive atmospheric features in the solar system, not because it is dramatic in appearance, though it is, and not because it has generated public fascination, though it has, but because it sits at a parameter value that makes the fundamental physics of rotating atmospheric instability visible at planetary scale. It is a natural experiment running continuously in the atmosphere of the sixth planet from the Sun, whose results are available to any instrument we care to point at it. Voyager read the first page of this experiment in 1981. Cassini read the next 40 pages in detail between 2004 and 2017. JWST has just revealed that there are more pages than we suspected, and that they describe processes we have not yet named. Future Saturn missions will continue the reading. A mission capable of deep atmosphere probing will tell us whether the hexagon's roots extend thousands of kilometers into Saturn's interior. Further JWST observations of Saturn's upper atmosphere, planned by the research team that made the initial discovery, will determine whether the dark beads and the star pattern are persistent features or transient ones, and what their relationship to the solar wind and to Saturn's seasons turns out to be. Atmospheric models of increasing sophistication will attempt to reproduce the JWST observations from first principles, testing candidate mechanisms and ruling out those that fail to match the data. The process of science will continue, as it always does, by building more detailed questions on the foundations of previous answers. And somewhere above Saturn's North Pole, the Hexagon will continue to rotate with its 10-hour, 39-minute, and 24-second period, unchanged by our study of it, indifferent to the instruments we train on it, neither troubled nor inspired by the decades of scientific attention it has attracted. A pattern drawn by physics into the atmosphere of a gas giant, sustained by the geometry of a rotating shear flow, rooted in a deep interior we cannot directly see, and reaching upward into an ionospheric environment we have only just begun to examine. It was there before we knew to look for it. It will be there long after the next generation of spacecraft has arrived to continue what Cassini started and JWST has newly complicated. The Hexagon does not keep secrets deliberately. It simply exists in a universe that turns out, every time we look more carefully, to be larger and more intricately connected than the previous look suggested. We have been studying this shape for over 40 years, and the most important thing the James Webb Space Telescope has confirmed is that we are still, genuinely, at the beginning. Sleep well, wanderer. Saturn's hexagon waits, patient and perfect, in the dark.